My name is Alan Calvitti. I'm a data scientist, and my presentation today is on my book called Functional Data Workflow, which will be published by Wolfram Media. My name is Alan Calvitti. I'm a data scientist, statistician. My background is in engineering, actually. The title of the talk is a tour of functional data workflow, the book, the videos, the coding camp. So this is the book that Stephen Wolfram just approved for publication in Wolfram Media. This is a book that we've been working on for about 5 years based on our work at the Veterans Administration, University of California, and I'll tell you a little bit more about it. So that's a book title. The subtitle is Practical Methods with a Time Motion UX Case Study, where UX means user experience. That's a field in itself. I'll tell you a little bit what motivated this book and how the chapters and content in it. Most of the book is focused on one particular case study that comes from healthcare. And then, really the enabling factor is that we can use functional programming and pipelining to make the code base a lot smaller than it would be otherwise. And then finally, we talk about the aspirational part, which is creating the tutorial videos and the coding camp. So the motivation is basically that many books on data science are pretty episodic in nature. Basically, there's a technique or a method that you want to showcase, and each chapter is essentially independent from each other. This book is a bit different in which this is an end-to-end coverage in all the data analysis. I was a lead data analyst for many years at Veterans Administration, so essentially, this book shows you how to go from almost the very beginning to the end in terms of importing data, cleaning, indexing, the statistical methodology, and even how to normalize the data. Yes? We hope by the end of the year. I can share some of the chapters if Wolfram agrees to it, because they're ready, but there's some cleanup stuff, so hopefully by the end of the year. So it's basically an entire arc of all the data analysis coverage that we need to do, including the prep work, which is very important. The reason it's significant is because the data actually came from a large data set and multi-year studies that we conducted at the Veterans Administration and University of California. So that led to actually some measurement that we got from this methodology, and also for some health IT prototyping that were derived because of the results that we got from it. Part of the motivation was also to showcase the Wolfram language to do data. So for example, my work got considerably easier when the functionality in version 10 came out. So from version 9 to version 10, it was almost like getting a whole new language where queries that would take 1 page or more suddenly were reduced by a factor of 5 or even 10 because of association and the query functionalities. So particularly for temporal data analysis, most of what I'm going to show you is temporal data oriented. So the Wolfram language lead to some amazingly compact codes that with operator pipelining. So I really want to make use that the Wolfram language is a terrific language for doing data. So the intended audience is for data scientists and professionals in this field, hopefully, certainly grad students, and I think that some advanced undergraduates could also get it. It's not really meant for beginners, really, because the prerequisites are you sort of have to know a little bit about functional programming, and you should have some exposure to the Wolfram language. So the topics that are covered in the book are, we go through the entire thing, even the metadata management and how we use Google spreadsheets, for example, to do an agile cycle in which we develop the data dictionaries, for example, online as we were actually doing the study. Nothing was given to us. We couldn't afford a DBA. None of the data was indexed. We had to come up with everything for ourselves. So it goes through the entire arc of I/O, indexing, statistical analysis, visualization, and even the results management. This book, per se, is not really focused on the mathematics or even the statistics. To be honest, there is some statistics, of course, but there's nothing about machine learning. There's nothing about big data, really, in this chapter, except for one chapter, and I'll tell you about these excursion chapters that I peppered in all over the book. So, for example, there is one chapter, which was the very recent FICO, the credit rating company. They have an explainable machine learning challenge with like 10,000 rows of data. So I used that and added that. That's a little bit more mathematical, but it's really not the focus. So yeah, so the excursion chapters are designed to basically be self-contained. Sometimes they tell you little bits and pieces about how to use Mathematica, but basically, you could take them or leave them, essentially. There's some typos there. Self-contained things. Okay, the functional code library, so I have an appendix which is a set of utilities. It's mostly a set of functions and operators that are mostly like one-liners, and that really showcases the power of the language when you see how quickly you can do some of these development here. Let me open up, let's see if this works. So this is basically my, it's not the finished product, okay, but this is sort of my code, and just to give you some example of the kinds of functions that are in here. These are all basically like related to associations and data sets, okay? But for example, or things to do with time objects, data objects, and so on. So you can see how small most of these functions are. I mean, I kind of avoid doing like unit testing for most of these things because they're so stable. Once I wrote them, there's very little work that needs to be doing in terms of maintenance purely because of their small size. Okay, so I'm not going to go into this in detail, so let me close this actually. Maybe if there's time, I can get back to it. Okay. All right, so I think we covered most of these. Oh, then the final sort of feature of this is that we're going to be using the Wolfram data repository to manage most of this data. Currently, it's sitting in Wolfram Cloud. I'm sorry, in Google Drive, basically. So most of this data and the code can be shared to Google Drive. But the advantage of the Wolfram data repo is that I think you'll be able to query some metadata around it. Okay, let's get through. All right, so let's show you some of these. Oh, actually here, while I was working on the slideshow, I realized that I'm going to import a couple of chapters. So I'm going to show you some of the difference because people don't understand that the distinction between querying on data sets versus querying the raw associations. Okay, so here's an example where I'm importing, there's something like 30 chapters. Here I'm importing the first 3, for example. Okay, so the first thing I'm doing is essentially creating an association where I'm giving the chapter numbers. And then the values are in an association, those are the keys. And then the values are the paths that I'm going to import. So this is the query, okay? I start off with file names, and then I grab the first 3, so that's a query. And then we do an association map, which does nothing in this particular case, because really the hard work is just taking key map, and I'm gonna strip out, it basically starts off with this as the input, and then I just basically split it up by the path components. And then, of course, I take the last component of that, then I split it by the dot up, the period, and then I grab essentially the chapter number from that, okay? So this is how you would query associations. So this shows that you don't necessarily need data set per se, but you do have to have all sorts of queries. So what does querying on data set bring to you? Well, it's a wrapper that sort of does formatting for you. There's a type system built into it, and it also lets you do query, it lets you compose queries very nicely in terms of the syntax. So you can see that basically what I'm highlighting here is the same as what's above here. It's exactly the same thing. But you can see that the syntax is a little bit more compact. And often you don't have to wrap things inside of the keyword query. All right, so the chapter headers, basically, I have some introductory chapters, and I'm going to label the excursion ones in green. Then, what I think is, the key thing for data scientists to understand is like, before you get to the machine learning, there's a lot of prep work. Yeah, so there's a lot of these chapters, and again, these are cumulative, right? They just, you sort of need chapter 4 in order to go, and they're progressive. Okay, so a lot of these chapters are about sort of like indexing and normalizing the data. Then there's a set of analysis chapters, and this is really the statistics and visualizations proper. And again, except for the excursion chapters that are sort of like self-contained sort of things. And then, like I said, like there's a concluding chapters and an appendix that includes the code libraries. So I have a code library that is the utilities that I just showed you, plus there's a project-specific code library. Okay, I'll open these later if we have time to actually show you the chapters themselves, but I just want to get through the slideshows here. Okay, so the study is significant because it's based on a study called Quantifying EHR Usability to Improve Clinical Workflow, EHR being electronic health records. The significance, let's see if these are openable here. So it was part of a series of study that we did for about 6 years. It's interdisciplinary, so it relates to operations research, clinical informatics, usability, human factor analysis. The idea is to measure doctors' workflow with time at task, and then also computer use. What functions did they use? And as part of that, navigational efficiency, how long would it take a doctor to order a medication, something like that, yeah. And then we had to do this at 2 different sites that use 2 different computer systems and 2 different institutions with completely different workflows. So you can see that that was the hard part, actually. Yeah. So we published a paper last year. I was the lead on that. Journal of Biomedical Informatics, if you want to get the details on the methods. the point of the book is not about the methods or even the results, okay? It's really about the software and creating these pipelines. So this significance is that it's a real world data set. It's not a toy data set. There's a lot of, it's not particularly large. It's less than a gigabyte, I believe, of raw data. Keep in mind, raw data was actually videos and all sorts of image capturing, screen capture. That's all identifiable data, so it's not even exported outside of, it's in a VA firewall. A lot of human coding was needed to get discrete behaviors and so on. I'll explain a little bit of that. But we shared these results with various Veterans Administration national initiatives to improve the health IT. They really liked the results, and in fact, it was even cited in Congress. And then we actually used some of these results to do some HIT redesign. Here's an example of how much data was collected. The vertical axis is the number of days, so it took us about almost 3 years of data collection. The red is like at the Veterans Administration in San Diego. The Qs are the visit identifiers, basically, the clinical visits. Each visit is basically one doctor, one patient for primary care and some specialties. So maybe like 50 doctors, 60 doctors, I forget exactly, and each doctor would see something like 5 to 6 patients on average, let's say, right? So, but each visit was basically in one room. Okay, so this is just to show you how much effort was involved, and if you don't do this, you don't have the data. Okay, all right, so the data is divided into, I'm gonna show you some of these data layers here. So for example, here's an example of how you can use cloud tools. This is a Google spreadsheet where they're showing some markers related to clinical codes for diagnostics, and these are ICD codes. And we would define these as we went along. We didn't have these from the start. So these are data dictionaries that we would actually have meetings, and while we would do the meetings, we would say, are these columns sufficient to spell out these data dictionaries? And if somebody, our team was very widely distributed. We had multiple faculty at various universities. We would be on call, and we could all co-edit these spreadsheets, right? So rather than hiring a DBA to do the schema ahead of time, we would actually create these spreadsheets. And then, of course, you have a lot of hard work at analysis time because none of this data is really schematized or typed. But basically, this is the kind of stuff that we'll work on. So this is an example of a data dictionary. Here's an example of some. Oh, okay. So all these data sets are in Google Drive currently, as I mentioned. So it's a tree, right? None of these are really, they're not tables in a database. But basically, at the end, you have branches of data, and then you have individual like CSV files. So that's how simple it is. And each CSV file depends really on the data layer, but essentially everything is generated as a tree. I'm gonna skip some of the details regarding how we actually got it, but there was a lot of human coding involved, a lot of video review and things of that nature. So here's an example of a human-coded clickstream file. So in other words, a person had to sit there and hand code every single mouse click with what are they actually doing on the computer. Right? And so these are also ragged. So these are very semi-structured pieces of data. You have a timestamp, and then you have some markers that are introduced by the recording software called Moray. That is a pretty common software to use to do these kinds of data captures. But then the humans have to go through, the human coders would additionally tag other pieces of information. So you can see that this is actually like pretty ragged in terms of a CSV. And then, so we have these data indexes here. So here's an example. And again, this basically mirrors the file system. Yeah, so this actually just shows basically just the folder level things, not the actual data. So you don't see the individual CSVs, but basically you can think of at the leaf nodes here, there's almost like 100. If there's 200 visits, you would have 200 files associated with each one of the leaf nodes. I'm sorry that's a bit small here, I'll make it bigger. And by the way, this is basically like a one-line function to mirror the file system into this. Okay, which I think is pretty incredible. You can do these recursive queries, and they're very fast. Yeah. And here's an example of the data dictionaries. So, what I learned in the 5 years is that it helps to just organize all your project data into one tree, essentially. If you do that, then it's a lot easier to keep track of where things are. You can just kind of key into the branch that you want much more quickly than if you have everything scattered around. Oh boy, let's see. Okay, so here's the actual meat of the. Here's a figure that we published. This is in the Journal of Biomedical Informatics. This is what we actually collected. This is an example from one example visit. And this is the kind of data that we collected. So in part A, we have mouse path activity. So basically, the XY coordinates of the mouse. So this is for 30-minute visit. So during a 30-minute visit, the doctor may or may not be actually using the computer, right? They're probably with the patient. They're doing physical exams. But when they're in front of the computer, you can tell when they are because the mouse is moving. Yeah, so when it's static like this, they're probably with the patient and so on, right? So the mouse is moving, Then there is mouse activity. Now this is human coded, and it's human coded into a set of discrete behaviors. So in other words, what are they actually doing on the computer? Which window are they in? Are they in the notes? Are they in order entry, consults, and so forth? So that's this channel here. Then we also have what they actually typed, and we have to de-identify it. So we have to normalize away what they actually typed into a set of characters. For example, what we really wanted to know is how much numeric data are they entering in the notes? Because numeric data is probably something that they copy-pasted from a menu or system, and that's something that should have been automatic, but instead they're actually copy-pasting it manually, potentially leading to errors. So we really just wanted to discriminate alphanumeric versus control keys and that kind of stuff. Then we have eye tracking. We had eye tracking device to see, did they skip some information? That turned out to be very difficult, actually. And then we have a set of, based on room video, we have who's speaking. That's these channels here. Actually, let's see. Yeah, so this is who's speaking when. So literally we had microphones, and from the audio, somebody had to tag the doctor is talking, the patient is talking, and so forth. And then we have some additional information. Eventually, you lead to these sort of continuous behaviors, and that's how you do the time of tasks, essentially, once you have this. And we also look, this is actually one of the most interesting ones, is the nonverbal. This is, what is the doctor actually looking at? Blue is when they're looking at the computer monitor. Green is when they're looking at the patient. Pink is when they're looking at medications or paper. And there's also physical exam and so forth. So for this particular doctor, you can see, first of all, there's a lot of back and forth, but when you kind of mentally integrate it, these guys are looking at, in a 30-minute visit, they're spending 15 minutes or more looking at the computer. They're still talking with the patient, but that's how intense the workflow is for a lot of these doctors. Okay, so I have 10 minutes left, so I wanted to get to some of these functional patterns here. I think I can kind of skip this. The idea is that with functional programming, often you can just use operators. You don't have to carry the arguments with you most of the time. You can do things that are, for example, like in databases, you do joins, but with hierarchical data, you can do merge and on the key value dictionaries. And when you do merges, you can actually pass a function, unlike join. So when you do a join, basically, the keys are already defined for you, but in merge is a much more powerful idea. So that's an example of an operator that takes a function as an input in addition to the data. And you can create some very, very fancy things. So this is more like computer science things. This is all spelled out in the book, so I'm not really going to get into it. But it basically leads to much more scalable and usable queries that you can change if as needed. And like I say, I think most people are not aware of this, but basically the Wolfram language, I work with people that used R, a biostatistician used R, and another programmer used Python. And the features that are in the Wolfram language let you do things in much less time, basically. That's the bottom line. Fewer lines of code, much more easier to read, and so forth. Provided that you're familiar. It took me a good 10 years to move from like a C and C++ mentality as an engineer to using to thinking in terms of functional programming. Once you make that switch, it's very difficult to go back, okay? Just because of the efficiency. And I would really highlight among them is just you can think in terms of these query pipes, basically, where you have, these data flow languages are basically, you have these directed acyclic graphs where you have input data at the initial stage, and then you create various intermediate stages of data until you finally get a final data set. Pretty much like Git commits, essentially, it's the same sort of thing. I think I'm gonna skip this one. But yeah, okay, so one of the things I really want to emphasize, instead of having a function for every detailed piece of thing you can do, by using pipelines, you can actually create sentences of functions, basically, right? So you use patterns, essentially, and it's a much more flexible way of doing it. It really reduces the number of functions that you really need. I'll probably use a very small set of core functions that are generic kind of programming functions, but you can combine them very flexibly to create these programming pipes. And of course, the book is full of examples around this. So let me show you some of this. Probably have a few minutes left here. So here's some example queries. Okay, so this is from the index. In other words, even this is prior to even importing the data. This is how you would actually create. This is basically a census of how much memory each data layer takes up. Okay, and this is it. This is the entire query. The index was that tree that I showed you earlier. Okay, so basically, just like in a few lines of code, you can do some significant analysis. Okay, again, try this in Python. Get back to me, in a couple of pages later. Here's an example where you can kind of scale up these queries to do the same query on different population groups, for example. Okay, so this is an example of a NASA, what's called a NASA survey task load index. So you can do this, and you group it by, this is the VA side, this is the University of California side. And you're doing essentially the same query. You're just doing this quantile statistic here. But the point is now you can do it for multiple populations with the same query, and you just say all, and then you specify the query at the second level, and you have it, and it works like a charm. And you can see how small the query is itself. Here's one where we do demographics, and you can kind of create these dashboards. So easy to communicate results when you do this, rather than having sort of either very basic. Okay, I think I'm towards the end of this. Okay, so I'll just give you one more. Outer products. So here's an example where I created an operator called outer that works for key value pairs. And here's how you would do it. You can actually manage both the key pairs and the values. And now here, so scatter plots plus correlation. And this is it. This is the actual query. Now, of course, I had to do some intermediate results here. But basically, most of these queries are kind of like a couple of lines long. Okay, if you learn this sort of language. Let's see if there's one more that can kind of do it. Okay, the rest is basically just things that you're going to find in the book no matter what. But just to impress you, again, this is really just to again, highlight that it only takes like a few lines of code to make all these. Yeah. Time of task. So basically, this is the bottom. This is the kinds of things that we actually publish. Yeah, the time of task. How much time does it take you to, on average, how much do doctors look at the computer versus how much do they look at the patient by specialty, by site, and so on. Yeah, that's basically it. So. Oops. I can probably stop here, actually, because basically the end is that once we publish the book, I'm going to do a set of tutorial videos where I'll take a query and I'm going to break it down with echoes so that you can see the intermediate results. That should be fairly easy. And then we want to do something that's in between a MOOC and a coding camp. I favor coding camps because you can work in teams and you can work on real-world problems, which I think is going to be the future of instruction and education, rather than a MOOC, which is kind of like online and it's sort of like individualized work. Yeah, so basically that's it. Thank you.